Each of these lighthouses contains enough radioactive strontium to contaminate a small city, built by Russia, then abandoned. Russia built more than 1,000 of them, scattered them across the Arctic, and then simply walked away. Picture a steel tower frozen against a violet sky. Snow has buried its lower third, ice welded its door. No keeper has climbed its stairs in nearly 30 years. Yet deep inside, a small ceramic pellet still glows, still humming with invisible energy, still feeding a lamp that no ship has needed for an entire generation. The lamp itself burned out long ago, but the reactor that powered it somehow still has not. Why would any nation power a single light bulb with the same physics that drives a nuclear submarine? That question opens the door to one of the strangest engineering stories of the entire 20th century. To understand it, you must understand the geography. The Northern Sea route stretches 5,600 kilometers. It runs along the very top of Eurasia, the shortest maritime path between Europe and Asia ever charted. For most of human history, it was also the most impossible. 6 months a year, the sun never rises. Temperatures collapse to -50 degrees Celsius. Pack ice grinds against any steel hull that dares the passage. There are no cities. There are no roads. There is no electrical grid, only tundra, sea, and dark. In the 1960s, the Soviet Union decided this Arctic coastline would become a working highway for the empire. Nickel from Norilsk had to move. Timber from Siberia had to move. Nuclear submarines had to resupply in secret harbors. Ore convoys had to find their way through corridors of moving ice, guided by beacons in the polar night. These beacons marked shoals, headlands, and the mouths of frozen rivers, reference points where nothing else could be seen. Soviet planners drew up a list: 132 autonomous lighthouses along the Arctic edge of the empire. From the Kola Peninsula in the west to the Bering Strait in the east, across the entire Arctic frontier. Each would have to operate alone, in conditions that would kill a human being in under an hour. But here's the thing, no power line could reach these shores, no grid could be extended that far north. The nearest substation might be 600 kilometers away, across permafrost that swallowed any pole sunk into it. The Arctic refused infrastructure. So engineers turned to the only fuel they could deliver by sea, diesel. They installed generators inside insulated huts and assigned crews to tend them. And almost immediately, the system began to fail. Diesel froze in the fuel lines at -50. Lubricating oil turned to wax. Batteries cracked open. Surviving generators had to be refueled by helicopter, a single run costing more than the cargo ship below. Worse, the keepers themselves began to die. Winter isolation broke men. Storms cut off resupply for months. Suicides climbed. Heart attacks went unanswered. The Ministry of the Merchant Marine quietly concluded humans could not live here. The lighthouses had to become unmanned, autonomous, running on a power source that needed absolutely nothing at all. No fuel deliveries, no human attention. No moving parts that could freeze in the killing polar dark. A source that would sit in its tower producing electricity year after year while the Arctic tried to kill it. The solution was already orbiting above the Earth, a navigation satellite called Transit 4A, launched in '61. A device producing electricity not from sunlight, not from chemistry, but from the heat of radioactive decay. Inside the device was a pellet of plutonium. The pellet was warm because its atoms were quietly disintegrating. Channeled through thermoelectric junctions, that warmth generated a steady current. No turbines, no pumps, no moving parts, just a hot lump of metal and the patient mathematics of physics. A radioisotope thermoelectric generator, an RTG. Soviet engineers, watching from Moscow, recognized exactly what they were looking at. The principle is almost embarrassingly simple. Join two different metals, heat one end, and a small voltage appears across the junction, the Seebeck effect. Discovered in 1821, it is inefficient. Most of the heat is wasted, but utterly reliable. Nothing to wear out, nothing to break. You only need a heat source that will not stop. A radioactive isotope is exactly that, a heat source that cannot be turned off, unplugged, or humanly exhausted. For Soviet lighthouses, the chosen isotope was strontium-90, a byproduct of nuclear fission abundant in spent reactor fuel. Its half-life is 28 years, meaning after 28 years it still produces half of its original heat. Compress that strontium into a ceramic pellet, encase it in stainless steel, wrap the steel in lead shielding, surround the lead with depleted uranium, and you have a power core the size of a beer keg. That core glows with usable warmth for the better part of a century. The standard unit was called Beta-M. Beta-M weighed 250 kilograms and produced a modest 10 watts of usable electricity. It was guaranteed for 10 years, yet in practice many of these units quietly ran for a full 30. 10 watts seemed harmless. 10 watts will not power a kettle, will not even brighten a household lamp today. But 10 watts, fed through a sealed lead-acid battery and a flashing bulb, marked a headland across polar night. The genius lay in restraint. Engineers did not power a city, only one deliberate flash every 6 seconds. Visible across 20 nautical miles of black water from a device still running after its last engineer was dead. Now here is where the story usually gets told wrong, and the popular version goes something like this. The Soviets, drunk on atomic enthusiasm, fitted nuclear cores onto everything, icebreakers, lighthouses, even tractors, because they could. It is a tidy narrative. It is also completely wrong. The real reason is colder than ideology. In the 1970s, no other technology could do this job. Solar panels then produced nothing under polar conditions. Above the Arctic Circle, the sun vanishes for months, then skims the horizon at only a few degrees, casting weak, oblique light that early silicon cells could barely convert. Snow buried the panels, ice cracked their glass. Wind turbines were no better. Arctic storms snapped blades like matchsticks, and rotor ice tore each machine apart. Batteries alone could not last the winter. Fuel cells remained experimental. Geothermal was geologically impossible across the route. The RTG was not chosen because engineers loved radiation. It was chosen because it was the only physics that worked. And it worked beautifully. By the late 1980s, nearly 1,000 radioisotope generators dotted the Soviet Union. Most stood along the Arctic coast. Others powered weather stations, military beacons, and unmanned navigation buoys across Siberia. They needed no fuel, they needed no visits. They quietly converted nuclear decay into steady, unwavering navigation light. For 2 decades, the system worked exactly as designed. Then, the empire that built it ceased to exist. In December 1991, the Soviet Union dissolved. The ministries funding these Arctic lighthouses quietly dissolved with it. Maintenance budgets evaporated. The technicians who knew where each generator unit was located retired, emigrated, or quietly died. The master registry, every RTG, its location, serial number, installation date, was incomplete from the start. Classified for security, partially lost. By the mid-1990s, Russia could not say how many remained. This is the moment an engineering triumph became a slow-motion catastrophe. The lighthouses themselves began to silently decay. Roofs collapsed, doors rusted off their hinges, lead shielding cracked, and in some regions an even darker force arrived: scrap metal thieves. The economic collapse of the 1990s had created a black market for salvageable steel and lead. Remote Arctic structures, undefended and unwatched, quickly became targets. Thieves rode to coastal beacons in small fishing boats. They climbed the towers. They cut into the housings with hand tools. They had no idea what was inside. What they found, in many cases, was a warm metal cylinder. Warm in an Arctic winter, itself a quiet miracle. Some thieves stripped away the lead shielding to sell as bullion, leaving the bare strontium pellet exposed to open air. Others tried to drag the entire core away, abandoning it on a beach or a riverbank when it proved too heavy. By the early 2000s, unmonitored radioactive sources began surfacing in strange places: shorelines in Sakhalin, scrapyards in Murmansk, half buried in tundra along the Kara Sea. Each one capable of delivering a lethal dose within hours of bare contact. But here's the problem. The Arctic is vast and these objects are small. A 250-kilogram cylinder at planetary scale is invisible. Authorities knew there were missing units. They could not always know where those missing units had actually gone. The world learned what this meant one December night, 2001, in a forest near a Georgian village called Lea. 3 woodcutters were working in the mountains. The night was bitterly cold. They were looking for shelter and for warmth. In the snow, they found 2 strange metal canisters, each about the size of a thermos flask. The canisters were not just warm. The snow around them had melted in a circle more than a meter wide. The men did what any cold human being would do. They carried the canisters back to their forest campsite. They set them on either side of where they slept and used them as space heaters through the long night. What they did not know was they had stumbled upon 2 abandoned strontium-90 cores from a Soviet radioisotope generator. That generator once powered a remote Caucasus facility. When decommissioned, the cores were hauled into the forest and left. The Soviet Union no longer existed. No one came back. Within hours, the 3 men felt dizzy and nauseous. Within days, their skin began to ulcerate where it had touched the canisters. They were hospitalized in Tbilisi. The wounds did not heal. They deepened into radiation burns that ate through tissue down to the bone. The International Atomic Energy Agency was called in. Investigators traced the radioactive signature back to its hidden source. They recovered the canisters and confirmed a stranded RTG core, one of countless units scattered across the former USSR. 2 of the woodcutters survived, scarred for life. 1 did not. The Lea incident would change everything that followed. Within months, Russia, the IAEA, the US Department of Energy, and Norway launched a coordinated Arctic recovery program. Their mission: find every remaining radioisotope generator in the former Soviet Arctic and remove it. The work was slow, it was expensive. In many places, it was almost physically impossible. Teams flew helicopters to coordinates that proved wrong. They dug units out of frozen sand. They lifted cores from collapsed towers using cranes mounted on naval vessels. Recovered sources traveled to Mayak in the Urals, where the strontium could finally be safely processed and stored. Between 2001 and 2025, over 900 RTGs were recovered from the Arctic, Siberia, and the Russian Far East. The number unaccounted for is small, but not zero. Officially, the recovery program is nearly complete today. Unofficially, the Arctic is large enough to keep secrets for a very long time. Some still wait in silence. So why did Russia abandon the lighthouses? Why did the most ambitious autonomous lighting system ever built simply end? The answer is not that the physics failed. The physics worked perfectly. The pellets are still hot. The Seebeck junctions still generate current. Inside any of those towers today, a power source still hums quietly, doing exactly what its designers intended 50 years ago. The reason for abandonment is economics, not failure. And it is also progress. Since the first Beta M unit was installed, low-power lighting has been transformed. A modern light-emitting diode produces the same navigational flash using 1/100th of 1970s incandescent electricity. Modern lithium iron phosphate batteries survive Arctic winters that would have destroyed any battery available to Soviet engineers. Solar panels have improved by orders of magnitude in efficiency, producing usable current even in oblique polar light. Wind generators have been redesigned with ice-shedding blades and active heating elements built into their rotor hubs. A hybrid system of small solar arrays, a modest wind turbine, and a lithium battery bank works year-round. It powers an unmanned lighthouse in the same locations where Soviets once needed a nuclear core. It costs less, it is safer, it does not become a weapon if forgotten. So Russia walked away from the system. It did what every nation does when a technology is superseded, building a new system entirely. Today the lighthouses of the Northern Sea route still flash. They mark the same headlands and guide convoys. But behind their lenses, the warmth of strontium has been replaced by the cold efficiency of silicon and lithium. The atomic age, in this small corner of human infrastructure, is finally and quietly over now. Or is it? The Arctic is changing faster than anywhere on Earth. The polar pack ice is retreating. Climate models predict that by mid-century, the Northern Sea route may stay open for half the year. The geopolitics has already shifted. China has declared itself a near-Arctic state, eyeing the new northern corridor. Russia is rebuilding its northern fleet and steadily expanding its polar ports along the entire Arctic coastline. Container ships and liquefied natural gas tankers already move along the route in numbers unthinkable a decade ago. New traffic demands new navigation aids, hundreds of beacons, weather stations, and emergency response nodes along the coast. Solar plus battery handles most locations, but in corners of the Arctic, the polar night is simply too long. Storms are too violent, resupply too expensive for any system depending on ambient energy or visiting technicians. For these locations, engineers are quietly reconsidering nuclear power, not the heavy strontium cores of the Soviet era, but small modular reactors and modern radioisotope batteries with passive safety, tamper-proof shielding, and full satellite telemetry.
Russia has deployed a floating nuclear power plant, the Akademik Lomonosov, supplying electricity to the Arctic port of Pevek. China has announced plans for similar units to support its expanding polar ambitions across the high north. Designers study microreactors small enough to power a single research station or a cluster of navigation beacons. Fuel sealed for the operational lifetime of the unit, full remote shutdown capability, decades of unattended service. The atomic lighthouse, it seems, may return. It will look nothing like its Soviet predecessor tracked from orbit, impossible for a thief to open, retrieved at life's end by a vessel that knows where it lies. But it will, once again, be a small nuclear heart beating quietly alone in the deep polar dark, lighting the way for ships that depend on its silence and its endurance through the long polar winter. History, in other words, is preparing a second draft of this story, with lessons carved into its margins. The first draft ended in abandonment, in lost coordinates, in radioactive cylinders abandoned on a remote Georgian hillside. The Arctic is opening again. The lights must follow. The original question now demands a serious modern answer. Why power a lamp with a reactor? Because nothing else can burn untended for a century in darkness. The lighthouses themselves, the original ones, still stand. Most are empty now, their cores carefully removed long ago. Their lenses remain intact. Their towers, painted in faded Soviet maritime stripes, lean into the polar wind. On capes and islands no tourist will ever see, they stand as monuments to a singular idea, that humans could plant a permanent flame in the most hostile environment, then leave it to burn untended. The idea worked. The execution outlived the empire that conceived it long before its quiet polar end. And the next attempt, when it comes, will be better, because of what was learned and lost. If these stories of ambition against impossible geography interest you, more films wait here about engineering that shaped our world. The next investigation follows the new infrastructure race opening across the Arctic as the ice retreats and great powers return. Subscribe to continue exploring how our world is actually put together.